Advanced Router Technology Part 8, Configuring Multicast Routing. And boy, am I excited to talk about it. You know why? Because I just finished recording a complete nugget on all the concepts of multicast routing. Now, I have nothing against concepts. Concepts are good. That's what makes the world go round. But you know, the world never turns unless you get some configuration in there. And that's all I plan to do in this nugget is spend this entire time talking about multiple real-world multicast configuration, and I should add in there, as they relate to the CCIE exam. Now, you can get deep into multicast, and it really is an interesting technology if you want to learn about the M-bone of the internet and how that all works. But really, what I want to focus on here is the technologies that you're going to need for the CCIE lab exam and to deploy this in your environment. First off, we're going to discuss PIM dense and sparse mode. That's one of the easiest things to configure, and also throw one in there called PIM sparse dense mode, which is a combination of the two. To configure those, it's one or two commands to make them work, and that's really all there is to it. That's why there's so much in the concepts of multicast routing. But we're going to get a little more advanced than that in this section and get into creating a multicast boundary, which is, you know what, maybe I don't want a multicast message to travel beyond a certain point of my network. Maybe it's because of network bandwidth. Maybe it's because it's a security boundary. There's a whole host of reasons. So I want to show you how we can stop either all multicast traffic or just certain multicast traffic from going across. We'll also look at a concept called auto rendezvous points, which allows your routers to pick a rendezvous point that's close to them and really load balance between multiple rendezvous points. It's a real simple concept, but one that can save a lot of misconfigurations in your environment because you don't actually have to type in the IP address of the rendezvous point. And then I'm going to also throw in frame relay considerations because a lot of times people want multicast to work across frame relay, and it does out of the box. However, it doesn't work the best across frame relay. I'm going to show you one command that you can use to tweak it and optimize it to work that much better. So we might as well snuggle up and get real comfy on this topology because it's going to be where we spend the rest of this nugget as we configure this network to support multicast routing. Now remember, multicast routing is all about the concepts. I'm going to show you some configuration and you're going to say, that's it? That's all there is to multicast routing? Well, yes, there's really not too much to the config, but the ramifications for your configuration can be devastating to your network if you don't do it correctly. So I want to make sure you know exactly what we're doing as we go through and configure each one of these four routers. Now, speaking of four routers, we have these four routers deployed in our network. A multicast source is sitting behind router 2. Now, that multicast source could be anything, a streaming audio server, maybe a video server. It could even be an imaging server. A lot of companies are using those to re-image their clients whenever one of those goes down, and a lot of the imaging servers use multicast. So regardless of what that source is, it's located behind router 2. Router 3 and router 4, they have a client out here, but they're not doing too much. So a lot of the configuration I've already set up on those guys because it's going to be exactly the same as router 1 and router 2. And that's going to be where all the action happens in this configuration. Now, the first thing you need to do when you start deploying multicast routing, and I'll start on router 1, is do one of the most forgotten commands in multicast routing. Global config mode, we type in IP multicast -routing. Enter. What's it do? Well, nothing. And everything at the same time. That's the reason it's so forgotten, is because it turns on multicast routing. All of the rest of this configuration is going to go in there, but unless you type this one command to start things off, none of it will work. And if you forget it, you'll wonder, what's going on? Why isn't it linking up like I thought it would? Well, it's because the power switch hasn't been flicked. From there, you're going to need to determine two things. One, what interfaces are going to run multicast routing, and two, what mode you want those interfaces to participate in. Now, in the concept section, I talked about two modes. There was IP PIM dense mode and sparse mode. Now, looking at router 1, we have three interfaces, and I didn't label the interfaces or the IP addresses in this topology because Really, in multicast routing, they're not all that relevant. At least the IP addressing isn't for the routing and the unicast routing table, because multicast builds its own routing table. I'll show that to you in just a moment. So I'm going to jump out of this global config mode and do a show IP interface brief. And let's look here. We've got serial 0/1, and looking at this topology, I labeled this M and P. These two interfaces are part of serial 0/1. It's a multi-point connection, so we could see that kind of deployment. And then over here, I have this as serial 0/0.2. It's a point-to-point connection from router 1 over to router 4. So looking back at our IP addressing here, that looks about right. I also have a dedicated HDLC link, and that's the serial 0/1 that's going between those two, so we can have some redundancy. And then behind the scenes, on each one of the routers, I've deployed the IP address 10 dot and then the router number 1, 2, 3, or 4 to represent its Ethernet network. So let's configure those interfaces. Let's say in this case, I want all of my interfaces to participate in multicast routing. And this is a big deal here, because the more you enable for multicast routing, the more interfaces you enable to participate. Number one, you have to think of security. Hey, that's a new network that can now tap in to the multicast backbone of your entire organization. Now, there's ways of putting limits on that and saying, well, they can only reach certain multicast addresses, but by default, they have access to the entire multicast backbone. So you really need to plan, when you're doing this, what interfaces have clients that need to participate in that multicast world. So we'll say all of them do. I'll get into interface Ethernet 1/0. And I'll type in the command to enable it, IPPIM, and from here we can type in, there's a number of arguments that we can use, but the main ones are sparse mode or dense mode. Or the one that I didn't mention in the concept nugget, but I'll bring up right here, it's the one I always like to use, sparse/dense mode. The reason I love this is because it gives you the best of both worlds. You remember from the concepts nugget, we talked about sparse mode and how that configures a rendezvous point to where I can say there's that single point on my network that I want to rendezvous with. And in this network, we'll go ahead and make that router 3 as our rendezvous point. But let's say, oops, I forgot. I didn't set this router up for a rendezvous point. Well, don't worry. As long as I configure dense mode or sparse/dense mode, the other routers will take care of it, and this router would run in dense mode. So it gives you the best of both worlds. Now, when you're thinking of the CCIE lab, again, make sure you do exactly what they're telling you to. If they're talking about make sure traffic is limited, you don't want too much traffic on the network, definitely lean towards that sparse mode, because yes, you do have to configure a rendezvous point, but that will make sure that you don't have any traffic coming from dense mode that doesn't belong there. But for consistency, I'm going to configure everything in our scenario for sparse dense mode. I'll go into those other two interfaces, serial 0/0.1, .2, and finally serial 0/1. There we go. You have to type that command in under each interfaces that you want configured for that. But oh no, I forgot. Did I get them all? Did I type it all in? Well, short of doing a show run, you can't tell too easily from a show IP interface brief command which ones are configured with the IPPIM command. There is a great command that I use all the time to make sure I got all the interfaces. It's show IPPIM interface. And by typing that, it will show you all of the interfaces that you've configured to support multicast routing. That's nice because I can quickly verify without having to go and weed through the entire running configuration what interfaces should be and are supporting the different PIM modes. So we should be good to go on router 1. Let's hop up to router 2. A hop, skip, and a jump away, and there I am on router 2. So I'll do a show IP interface brief here again just to familiarize ourselves. We look up here, we can barely see router 2 connected to the serial interface and the Ethernet network right there, and looks like our interfaces are matching up. Great. I'm going to type in IP multicast routing, turn on that feature, and we'll go under serial 0.1 to IP PIM sparse dense mode. We'll go under interface Ethernet 0, IP PIM, well actually just up arrow, sparse dense mode. All right, so we're good to go. I'll just do a show IPPIM interface to make sure that we're running that okay. We're version 2 of the PIM protocol, and it's running in sparse dense mode. We should be good to go there. Groovy. Now, Let's look back at our topology and let me give you tip of the day, number 1. Now, I have on my network a multicast source. It's a server that could be running IP video streams or audio streams, but let's think. We're thinking CCIE Lab here. Do you think you'll have a real server that's running a clean audio stream that you can tune into? Unfortunately, no. The budget's not that good. And I must tell you the truth, I cannot lie, I do not have a multicast source either. So how do we test this thing? I mean, it's fun to do the IP PIMs, get it all set up, but how do you make sure that these routers could reach that multicast address? Well, the way that you can do that is to go under the interface that is going to support that multicast address. In our case, it's going to be Ethernet 0, the one connected to the LAN right here. Internet interface Ethernet 0. And here's the command. IP IGMP join group, and then you get to type in the multicast group address you want that interface to join. Now, it's not as good as having a real multicast server, but it's almost as good. It's nearly as good. Because what we can do is we can type in this group number, because remember, these aren't specific IP addresses. All the clients will join this group. I'm going to type in, let me see if I remember it, 230.240.101. 230.240.101. Now, that interface has joined that multicast group and will respond to that group number if you were to ping it. Beautiful, because now we should be able to jump down to our routers and ping that IP address. Let me do that. I'm going to jump down to router 1, and by the way, the ping command, it sure looks weird when you do it for multicast. You'll feel just like things are broken when you see it, even if it's working, because it just looks different than what you're used to. Watch this. I'm going to ping that group number up there. And what I see, ooh, I just get the EBGBs every time I do that. It says reply to request 0. That means it's good. I've pinged. It doesn't give me my exclamation points. It says it took 88 milliseconds for it to respond to that ping request. And the response actually came from 192.168.1.2, which is the IP address of the serial interface up here. If it was not working, we would not get a reply. It would end up saying, sorry, cannot connect, and it would probably take a little bit longer to come back. So that's what the ping looks like when we ping that multicast address. Now, I'm going to show you the other show command. There's only 2 show commands that I use on a regular basis for multicast. The first one was show IP PIM interface, and the other is show IP mroute. Remember I had said the multicast creates a separate routing table. Well, it does, and sure enough right here, you see that I have a separate routing table that it's created for all of these multicast locations. A lot of these are default IP addresses, but 2 of them I want to focus in on right now, right here and right here, are from the IP address that we just pinged. Now, it's a routing table, mroute, that stands for the multicast routing table, so you're going to see a little bit more information than you may expect here. You might think, well, 3.1, that's this, or actually 3.1 is down here. That's this interface. How is that ending up in the multicast group? Well, by enabling all these interfaces for sparse/dense mode, remember, dense mode by default will start sending the multicast out all interfaces until it starts pruning it back. You see this? It started to prune off the interfaces that don't need that multicast, but you can see how it's starting to waste bandwidth. And if you remember from the concepts chapter, I said the multicast routing table will have the source IP address, the place it goes to get to that multicast, and then the multicast group number for dense mode. If you're running sparse mode, it will be represented by this star. The star means that you're pointing to a rendezvous point of some point. Now, in this world, we have both modes combined, and as of right now, it is running primarily in dense mode. Why? Because we haven't configured any rendezvous points on our network. We just set up IP PIM sparse dense mode and we said, go, do your thing. So since there is no rendezvous point, this router doesn't have any idea who that is. It's going to run everything in dense mode, which means we're going to send the traffic everywhere and slowly prune back the links that don't need it. Now, if your CCIE lab requirements said, you know what, you need to make sure that you're conserving bandwidth, then that's a big no-no. So we better take a look at how to configure our network to support the lower bandwidth utilization way, and that is going to be IPPIM's sparse mode, to where when we're looking at this network, it will only be advertised and sent down the links if those links absolutely need it. Essentially, it will be join requests that activate the links rather than just sending it and having it prune it back as it does with dense mode. So in order to configure sparse mode, we have to set up a rendezvous point. Now, I'm going to show you first off the way that, well, I'm not going to say I don't like it, but the standard way of doing the rendezvous point, and then we'll add a couple little fireworks to it. I'm going to say IPPIM followed by the command rp-address. Then we can type in the address of the rendezvous point. Now, as I mentioned earlier, router 3 in this network is going to be the rendezvous point, and its IP address is 192.168.1.3. So I would type that in here. I'd type in 192.168.1.3. On every single router, I have to do this command: router 2, router 1, and router 4. And if your network has hundreds of routers, that means hundreds of commands. Now, before I talk about some of the disadvantages of that, let's look at some of these options. First off, we have the ability to add an access list. This is pretty cool, because it allows you to have rendezvous points for different groups of multicast addresses. For example, let's say that router 3 up here was a rendezvous point, but my network had grown large enough to where I had a lot of multicast sources, and I wanted it to be the rendezvous point for maybe 225.0.0.0 through 226. 255.255.255. What I could do is I could create an access list, just a standard access list. You can see right here is the standard range, or the extended standard range, that, or I should say the expanded standard range, to make sure I don't confuse the access list types. I could define an access list that says just those addresses are the one that this rendezvous point responds to. And then I could do the same command down here and say that this one responds to 227.x.x.x through whatever range I wanted it to go to. So using those access lists, I can really designate exactly what multicast addresses those routers are going to respond to. That's very cool for load sharing. And you can see I can also use some named access lists as well, but notice this last one overrides the auto RP messages. What? Auto RP? What is that? Well, this is why I don't like the standard way of doing rendezvous point. By typing in IPPIM RP addresses, x.y.z, whatever address that you want to type in there. The reason why is it's a static configuration. Yikes! Anytime I think of a static configuration, I have a flashback to something like an OSPF virtual link where I mistype it, or that IP address changes, or some network redesign means that the IP scheme needs to be modified, so I have to go back and change all these rendezvous point addresses. Thankfully, there is a better way, and that is the auto rendezvous point. And as the name implies, this kind of points us in the direction of, wait a sec, these rendezvous points can take care of themselves. Here's the idea. Let's say I wanted router 3 to be the rendezvous point of my network. Well, in that case, I'm going to go to router 3. And I'm going to go into global config mode. And I'm going to type in IPPIM followed by, and there's two commands that I need to type here. The first one is this one. Send RP announce. You can see auto RP, send RP announcement messages. Send RP announce, followed by what interface you want to send this out of. And this will be the source address that these messages will come from. Now be careful. In this case, I only have one option. Router 3, it's going to be serial 0/0.1. That's the multi-point interface that connects it to this cloud. But let's say I was down here on router 4. In that case, what I really recommend doing is creating a loopback interface. We'll say just 1.1.1.1 and advertising that into the rest of your domain using whatever routing protocol. That way, if you use that send RP announce message, you can say I want to send it with a loopback and not bind it to either one of these physical interfaces. You have redundancy. So if one of these interfaces go down, it can automatically go through the other interface to reach that loopback. Loopback addresses are a handy thing. But in this case, I only have a single connection to the cloud, so that's okay. So send RP announce followed by that address, and then it says the scope. How far do you want that announcement message to go? It's going to be announcement. Hello, I am the RP. How far in your network do you want that to go? Do you want it to reach all the routers that are out there? Do you want it to have a specific boundary that it goes to? This is something that we're going to see in a lot of the multicast configurations, is the time to live of XYZ. In this case, it's the RP announce packet. Now, the time to live essentially says how many hops do you want this message to go? How many routers do you want this to travel through? Now, we have a fairly flat network. Everything's only one hop away. But imagine if I had 10 routers beyond router 1. I would set my time to live to be something like 11. So router 1 is the first hop, and then the 10 beyond. As soon as it reaches that 10th router somewhere out here in mystery land, the rendezvous point announcement dies. It will not go any further. Now, here's the consideration. Think of this in your network. In the real world, that's great for a security boundary. Nobody beyond that router is going to know about your rendezvous point that controls your multicast backbone of your network. But that's bad, because what if down the road, it's a year later, the network grows, you add a branch office and add router number 12 in the chain. Well, what happens? It doesn't receive those rendezvous point announce messages because it's 12 down, it's 12 away. And you're going to sit there troubleshooting, pulling your hair out, and then going, oh yeah, I set the time to live to die right here. It's one of those things that will come back to haunt you. So even though it's a good security measure to keep that announcement from going to a certain point, I would say set the scope a little further than you typically would to make sure that down the line, if you do expand, you don't end up having those routers not being tapped into the multicast backbone of your network. Now look at this. You remember the access list scenario that I showed you up here, where I can attach an access list to say it only is going to be the rendezvous point for these groups. Well, why not have it announce that with the RP announcement? Brilliant! Now the routers will take care of themselves, and what's better? We can now have multiple rendezvous points announcing what multicast groups they are responsible for by attaching them to an access list. You can also adjust how often that announcement interval is using the interval message. By default, it's once every 60 seconds, but I'm going to leave it at that default. That is the first step in configuring an auto RP. The second step is to configure what's known as a mapping agent. This is primarily for larger networks, but I'm going to type in send RP now discovery. See, here's the idea. This auto RP is designed for pretty large networks, to where we have the rendezvous point kind of announcing its availability, and then somewhere else on the network, it could be the rendezvous point itself, or it could be another router that's more well connected than that rendezvous point. You're going to have the discovery messages, or the mapping host, that says I'm going to be the host. Let's say it's router 1. I'm going to be the router that accumulates all the rendezvous points that are on the network and sends them to everybody else. Think of it like in OSPF, where we had the designated router. That router managed all the incoming messages and sent them to all the other routers. So you don't have this flurry of rendezvous points, or in that case, OSPF routers saying, hey, I've got all these updates. It's that same logic. Instead of having this flurry of rendezvous points all around the network, you're just going to have rendezvous points announcing to the mapping agent. Now, we could have the mapping agent be router 1, but since our network is so small, we might as well have router 3 be the rendezvous point and the mapping agent. I'm going to type in send RP discovery. That configures it to be a mapping agent. Don't really need to configure an interface. I'll just put scope followed by my time to live. I'll say 15 hops again. That now allows router 3 to be the rendezvous point and the mapping agent all in one. I don't know if you noticed this, but remember when I did the demonstration, we did the dense mode, and I did the show IPM route? You might have said, oh, okay, I see that, oh, it pruned it out of the table. I need to ping it again. Let me get that one back in the table. Ping, what was it? 230.240.100.1. 230.240.100.1. You can see my router kind of prune that out of there. So there we go. Should be back in my multicast routing table. So I'll do a show IPM route. You might have seen that one and gone, okay, that's great. I see it. Life is good. But what are these guys? 224.0.139? Scroll down a little bit. 224.0.1.40. I don't remember configuring those in my network. Well, here's the beauty. Those are the addresses that your routers listen to for RP announcements. Remember, I said we configure our rendezvous point to start announcing things out, announce, and say that it's available. Well, if nobody's listening, then what's the point? Here's the other big catch about rendezvous point auto RP features. It only works in the sparse dense mode. Remember, now you see why. Let me write it up here on the board. Sparse dense mode. I'll just put sparse-dn as a visual note for you. Sparse dense mode says it works in both. Sparse mode says I'm not going to send the multicast message until somebody explicitly requests it. Dense mode says I'm going to send it and then prune it back once I realize that nobody needs it. The reason that auto rendezvous point needs this mode is because the rendezvous point is going to start announcing itself. Hello world, I am the rendezvous point. Well, if we're in sparse mode, who's listening to that? Nobody. Nobody's listening until somebody explicitly requests it. That's why we need the dense mode features to say, I'm going to send that everywhere, and then people will prune it back as they need to. That way, that announcement will travel throughout the network and then get pruned back. These addresses, 224.0.1.40 and 39, that's what is used for the auto RP announce and mapping agent or discovery messages that we've seen. That's why we have to have the sparse dense mode configured. So we've got the two commands. We went on router 3 and configured it to be the rendezvous point, to send those announcements, and to be the discovery agent. Now there's one more. I know it looks like a lot of work, but it's really not. I'm just adding the explanations as we go. The final command that we have to type in here on router 1 and every other router that's going to participate in this is IPPIM followed by accept RP. Because I need to say to accept the RP addresses that are going to be received by the auto rendezvous point. We need to say you need to accept those auto rendezvous point announcements. Now I'm going to type in the command that we can use to verify this, show IPPIM rendezvous point and followed by mapping to see the group to RP mappings. Good. We have, the reason I get so excited is because those are sent once every 60 seconds. And if it wasn't there, I was going to have to pause the recording. Once every 60 seconds, those come out. So if you don't see this show up right away, don't panic. Give it at least a minute before you start troubleshooting. So we see the group that it's responsible for. There's our rendezvous point. Now what I want to do is I want to ping that address, 230.240.101. Ping 230.240.101. The reason I'm doing it again is now it should be going through the rendezvous point to get there. Now I see the reply, but if I do, let me just do a show IPPIM RP. Look at that. We have the group 230.240.101 going through the rendezvous point to get there. If I were to do a show IPM route, and I'll attach a summary keyword on there to trim that table down, what I see is that 230.240.1, I don't see that little source address anymore. It's gone to an asterisk because now everything is going through that rendezvous point address. That is how we can configure sparse mode on top of dense mode. And in this case, dense mode is only going to be used to advertise those rendezvous points to the network. Now what I'd have to do is I'd still have to go to router 2 and router 4 and say I want to accept those rendezvous point announcement, but that's just one command away. Dense mode is used to get that rendezvous point out to everybody. Then they will use sparse mode for all of the true multicast communication. Wow. All right, go ahead and sit back in your chair and take a deep breath. I want that just to soak in. Just how cool that kind of configuration is, integrating the best of both worlds. And I'll tell you what, if you actually sit back in that chair, lean back right now and just think, you know, it's pretty neat to see it implemented, but somewhere out there is a fellow or a lady who thought about how to make that work. It's humbling. It makes you really feel about as smart as a Kiwi by the time it's said and done to think that somebody out there really figured out how this whole multicast system works. All right, go ahead and lean back up because there's a couple more things I want to talk about, a couple quick tips on multicast security and boundaries, and then we'll go ahead and wrap this nugget up. First things first is that we can implement a security boundary or kind of a dead zone, if you will, for multicast to stop multicast packets from traveling too far on our network. For instance, let's say router 1 is a nice security boundary there. I'm going to go into the interface configuration mode on router 1, and what I'll do is I'll enter interface serial 0/0.1, which is one of my interfaces, and I'd have to do this for every interface that's going to be receiving multicast traffic. And there's two commands that I can use to implement kind of a dead zone for multicast. I'm going to type in IP multicast TTL-threshold, and by the way, in some iOS versions, this was a new one to me when I was looking at the commands I was going to use. Some iOS versions, it's actually just threshold. They don't have the TTL in front of it, so you'll have to check for your specific one. But this one allows you to set what threshold you're going to have for multicast traffic, how much you're going to subtract off of the time to live for multicast packets. If I have multicast packets traveling through my network and I want them to die here, I would implement a pretty high time to live. I'm going to say right here, 255 will be my time to live threshold. So by the time they reach this router, boom, they're in a dead zone. Now that kills all the multicast traffic that comes to this router, but I can get more specific than that, get a little more accurate and pick off the specific multicast packets that I don't want. I can say IP multicast boundary, and what I can do is employ the use of an access list to help me. I can say I want to have a boundary for certain ranges of multicast address. Maybe there's some multicast addresses that maybe CEO is having a video conference with the executive management. You don't want it to travel outside of that corporate network. You could go ahead and say, I want to pick off just the ones in that range. You'd have to define an access list, and I could actually hit enter right there and define the boundary at this router. You can see it also can filter auto RP announcements as well. If I don't want to set that scope too accurate on the router and limit my scope, I can actually set the boundary on each one of the routers so the auto rendezvous point announcements don't go too far. So that's the way that we can restrict those multicast addresses from going too far. All right, and the final topic, drum roll please, of this entire nugget is going to be the switch. How do we configure the switch to support multicast? I'm going to go ahead and open a session to one of my Catalyst 3550s. Oh, let me clear that line. And I've got an old iOS, so I have to clear it a few times on this access server. Ignore the gibberish that you see on your screen right now. My access server has got an old iOS version that's kind of buggy. All right, there we go. I'm on the switch. Let's talk about the switch side of things. When a switch receives a multicast packet by default, who gets it? Think about that. Who gets that multicast packet? What MAC address does it go to? Well, the answer is everybody gets it. It's just as bad as a broadcast. So if you don't configure your switches to properly support multicast, oh my goodness, what have you done? Because you're going to have multicast packets that tear your switch network apart. It's just like taking the routers out of this whole scenario. All of the multicast will be flooded to every switch in your network. So what you need to do, and this is why I kind of save this to the end, it's only one command. Just jump on your switches and type in IP IGMP snooping. Enter. There's no real arguments you need to attach onto it or anything like that. IP IGMP snooping allows your switch to participate in some of the layer 3 of multicasting. It will be able to see those multicast packets and which hosts are trying to tune into them. At that point, it can filter down those multicast messages so they only go to the ports that are requesting it. Without this one command, and boy is it a powerful one, your switches will send multicast packets to every port. It treats those packets just as it does broadcast. So by turning on IGMP snooping, which is the industry standard way, Cisco has a way as well called CGMP that does essentially the same thing. But IGMP snooping is the one you'd like to use. That allows you to restrict those multicast packets to exactly the ports that you want them to on the layer 2, the switch network. The final thing that I want to talk about, and I promise we'll wrap this nugget up, is going to be the frame relay considerations. And there's only one command that's specific to frame relay in this world. And that is for frame relay connections that do not allow broadcast or multicast messages. Now, on this router, I'll do a show run on my router 1 right now. You can see that I've set up my frame relay in the sense that I'm mapping the IP address. It's a multicast interface, and I always include this broadcast keyword so my routing protocols work okay and multicast work okay. 99% of the time that keyword will be there, but let's talk about the 1% that does not allow the broadcast or multicast messages. If you go under the interface, I'll do serial 0/0.1 that connects to the frame relay cloud. There's one command that you can type, IPPIM NBMA mode. That's the only configuration that's there. It says it's not recommended for sparse dense mode. It's recommended only for sparse mode. And what that does is it allows the multicast packets to travel through the network as unicast, as in this router will convert them to unicast as it goes across that frame relay cloud. Again, very rarely used, but if you ever get to a scenario that says do not allow broadcast or multicast to go across that cloud, you have to configure routing protocols to be unicast based, and in this case we have to have our multicast relationships be unicast based. That's the way to do it. IPPIM NBMA mode configures them to convert to unicast. So let's sum up this nugget and take a look at multicast routing, a technology that I think has a huge future as IP telephony and a lot of the newer technologies really take hold in our industry. In this nugget, we took a look at nothing but configuration, setting up multicast routing to work in the real world and specific to the CCIE lab. We looked at both sparse and dense mode, which we really looked at them together by configuring the sparse-dense mode on our routers and getting the best of both of those worlds. We looked at creating the multicast boundaries and configuring auto RPs. As a matter of fact, those were kind of moved somewhere up here when we talked about the full configuration of sparse mode. But multicast boundaries, stopping those multicast packets from going past a certain point in your network. We looked at the switch as well. I don't want to forget about that. The IGMP, it's only one command. The IGMP snooping to make sure that only the ports that are tuned into multicast will get those messages. And then finally, we hit the frame relay considerations, the IPPIM NBMA mode to convert those that communication over a frame relay cloud to nothing but unicast. I hope this nugget has been informative for you, and I'd like to thank you for viewing.